Hello, this is Mr. Stansbury. I'm going to take you through the notes on series. At the end of this, you should be able to say, I can use sigma notation to find the sum of a series given several terms and vice versa. Okay, so first things first. A series is the sum of the terms in a sequence. So we're going to take all the terms of a sequence, add them all up, and get a total. Okay, a finite series has a first and a last term, and will therefore always be some kind of finite real number. So like, for example, if the series was 3, 7, 11, 15, and 19, this is going to give us an actual finite number. Okay, an infinite sequence has a beginning but no end. So like 3, 7, 11, 15, 19, ... meaning it goes on forever and ever. In many cases, the sum of an infinite sequence cannot be calculated, but in some cases, it does actually converge. It ends up getting closer and closer to a finite number. Okay, so we'll look at some cases like that. All right, the sum of terms, u sub 1, first term, u sub 2, second term, u sub 3, so forth and so on, all the way up to u sub n, which u sub n in this case is the last term, can be written using sigma notation or summation notation. This symbol here, this little funny looking E, is sigma, okay, and that's why it's called sigma notation. Okay. We write u1 plus u2 plus u3, so forth and so on, all the way up to un as this here. We got our little sigma notation here, k equals 1 on the bottom and n on the top, and then we've got our u sub k out here. Okay, so this reads as the sum of all numbers of the form u sub k, where k equals 1, 2, 3, all the way up to whatever n ends up being. Okay, so that n is going to be the last term in the sequence. All right, for example, here's our little sigma notation. The k is our index of summation, it's called, and that equals 1. So 1 is going to be the first value of n. So when we go through and figure this the series out, then what we would do is we plug in 1 for n first, and then we plug in 2, 3, 4, 5, all the way up, and our last term is going to be 7, the last value of n. Okay? So if we were going to do this here, this is going to look like this. Plug 1 in for n, and that's going to be, let's see here, that's going to be 3, right? And then we're going to plug 2 in, and again, we're going to add these all together. So instead of putting a comma, I'm going to put plus. So then we put a 2 in. 3 times 2 is 6. That's the second term. So we even do this first, second, third. So the next number is 9. We're keep multiplying by 3. And then 12, 15. So that's the fourth, fifth. And then 18, sixth. And then 21 is going to be the last one. So this all here is saying, what does this all equal? Okay, let's take a look at example 22 here. Consider the sequence 5, 11, 17, 23, so forth and so on. Write down an expression for s of n, and then find s of 5. So one way we can obviously do this is with our little sigma notation that we just have been going over. So we write our little sigma here. We do k equals 1. So we'll start with the first term. And we're writing down an expression for s of n, not for any particular s of 5 just yet, so that means we're going to go up to n, and then we'll plug in a number for that later on. Okay, and then we got to come up with our equation piece in here. Now, we can use our, let's see, first off, we got to figure out arithmetic or geometric. We're adding 6 plus 6 plus 6 here. So we're adding 6 over and over, so this is definitely arithmetic. So we could use our little formula, u sub n equals u1 plus n minus 1 times d. So first term is 5. Number terms n is going to stay the same. And then our common difference here is 6, right? So we can distribute the 6 back through. un equals 5 plus 6n minus 6. So un really is going to be 6n. 5 and negative 6 is minus 1. Okay, so that's going to be 6n minus 1. Okay? Now, there is a different way that you can go about doing this without the formula. And the way I like to do this is say, okay, I know I'm going up by 6 each time. So if I'm going up by 6 each time, I know that this is going to be 6n. Okay? So now if I plug in 1 to this, 6 times 1 is 6. But I know that my first term is 5. So what do I have to do to 6 to get it back down to 5? I simply subtract 1. So I get 6n minus 1 that way as well. Okay? So you can do that either way. So that's one way to write it, is this here. Or I kind of like this way better. It's not writing it with a sigma notation, but it will make it a lot easier for us when we're going through to find the first 5 terms. Okay? So what we can do with this is now we can use our sum formula for the arithmetic series, right? So that is, we can use S of n equals n over 2 times 2u1 plus n minus 1 all times d, right? So we have this formula here. This will give us our sum of the entire series. This one here, the downfall of this is we actually have to plug in 1. Like to find S of 5, we have to plug in 1, 2, 3, 4, and 5. Find all those 5 terms, add them all together. This will do it all for us in one step instead. Okay, so since we're writing down our general formula expression here, we're going to leave n alone. But then we know that u1, our first term here, is 5. And our common difference is 6. So we'll simply plug those in. So we get, let me move this over. Okay, so I just moved it up there. So our first term is 5, our d is 6, and then since we're looking for the general expression, our n is going to stay the same. So we just write S of n equals n over 2 times u1, which in this case is 5, plus n minus 1, all times the difference, which is 6, right? So we're going to distribute that 6 back to both of these here, and we get S of n is n over 2. I'm going to actually write this as 1/2 n. You'll see why here in a little second when we're simplifying. 2 times 5 gives us 10. Distribute the 6 back here, plus 6n minus 6, and we get Sn equals 1/2 n. We get 6n, and then 10 minus 6 is plus 4. Okay, but then now we're going to want to distribute this 1/2 n to both pieces. So half of 6 is 3. N times n is n squared. So we get Sn equals 3n squared. And then half of 4 is 2. And then we patch the n on here. And this here is going to be a much nicer formula than this one here, because now when we're going on to part B, we're simply going to plug in 5 in for these n's here instead of having to plug in 1, 2, 3, 4, and 5 into this. We're going to show both, but I think you'll find that this way is going to be a lot nicer and easier. So let's first start off with this way. So we have our little formula here, right? And we've got k equals 1. Now for this here, now we know that n is 5, so we're going to put a 5 up here, and we do 6n minus 1. So literally we're going to plug in 1, 2, 3, 4, and up to 5 into this and get our 5 numbers, add them all up, and that's the sum of the first 5 terms. So plug in 1, 6 times 1 is 6, minus 1 is 5. Plug in 2, 6 times 2 is 12, minus 1 is 11. Plug in 3, 6 times 3 is 18, minus 1 is 17. 6 times 4 is 24, minus 1 is 23. And then the last one, 5. 6 times 5 is 30, minus 1 is 29. Okay, so we literally are going to go through and we are going to add these all together. So we probably want to get our handy-dandy calculator out. So enter those all in, push enter, and that gives us 85. Okay, so that's one way to do it. Or we can use this formula here, our S of n, just copy the formula down that we had from 3n squared plus 2n, and now our n is going to turn into 5, so we do S of 5 equals 3 times 5 squared plus 2 times 5. 5 squared is 25, times 3 is 75, 2 times 5 is 10. So that tells us that the sum of the first time 5 terms of 5 is going to equal 75 plus 10, which is 85, which is the same thing as that right there. Okay, we got one last example to do, but before we do that, let's take a quick little comedy break.
Those McDonald's fries are truly amazing, right? Has your mother ever made anything as good as a McDonald's fry? Not even close. We lie to ourselves when we eat McDonald's fries. We're like, oh, they're so thin, they couldn't be fattening. You ever eat too many McDonald's fries? Of course not! There's never enough of them. There's always that moment when you're eating McDonald's fries where you're like, what happened? Where'd they go? Then you start scrounging for the fry crumbs. You're like, oh, that's just a piece of paper from the straw. But it was touching the fries, so.
All right. Example 23, expand and evaluate. First thing we're going to do is expand, which means we're going to plug in all the integers from starting with 1 up through 6 into the expression k minus 2 squared. Okay, and then the evaluate part is we're going to take all those numbers and add them together. So first thing with expand, I made myself a little table here. K is going to be 1, 2, 3, 4, 5, and 6. So I'm simply going to plug in 1 into this expression and then 2, 3, 4, 5, 6, see what we get. So 1 minus 2 is negative 1. Negative 1 squared gives us 1. 2 minus 2 is 0. 0 squared is 0. 3 minus 2 is 1. 1 squared is 1. 4 minus 2 is 2. 2 squared is 4. 5 minus 2 is 3. 3 squared is 9. And then 6 minus 2 is 4. 4 squared is 16. Okay, so that part there is the expand. The evaluate is when we're going to take all these numbers and add them together. 1 plus 0 plus 1 plus 4 plus 9 plus 16 and see what that equals. 16 plus 9 is 25, plus 4 is 29, 30, 31. So the evaluate piece there would just be 31. Okay? All right, that's all we have for notes on the 5F series. If you have any further questions, please feel free to ask in class. Thanks.